Familiar with my background, I came to Cordova from the University of Alaska Fairbanks in 1994 to join the Sound Ecosystem Assessment Program. And the objectives of C were to determine the importance of physical and biological factors affecting production of commercially valuable fish damaged by the Exxon Valdez oil spill, including big salmon, Pacific herring. At that time, I was put in charge of studying the physical oceanography of Prince William Sound's fjords. So what I'm going to cover tonight for Simpson is going to be the baroclinic and barotropic currents and how they relate to exchange of water inside the fjord, and then evidence of internal tides and possibly lee waves from the hydrography, and then calculations I did about work and from tidal energy that's available to the internal waves. And it involves the mixing in the deep basin waters through the diffusivity. And I'll explain that more when I get to it. And then lastly, I'm going to show some advective processes shown by time series of temperature, salinity, and winds. So I was hoping to also talk about physical conditions affecting water exchange and some phytoplankton biomass in Zykov and whale, but I probably won't have time to go through that because by the time I talk about these other topics, it's probably going to be 45 minutes or more. And then I was going to show some examples of principal component analysis of freshwater contents in 94 and 96. Just a couple of examples. That was the first part of my dissertation work. What I'm talking about in Simpson was the second half of my dissertation. So Simpson is located in eastern PWS. I don't know if this is a bit blurry to you guys up there or not, but you can. It's
fun.
Okay. It's in the eastern side of eastern side of Prince William Sound, and just around the bend from Soundville Point, and Zykov and Whale are located in the south central and southwestern sound respectively. These three fjords differ significantly in physical oceanographic conditions due to variation in their geographic location, their basin morphometry, watershed characteristics, and the proximity to the allotment sources of glacial water that are affected through PWS every summer. Zykov, for example, is relatively shallow and influenced by strong currents in Hinchinbrook entrance, which cause mixing in its outer basin by vertical current shear, whereas Whale is located next to a prominent source of surface and subsurface glacial water with an icy bay. And I was going to cover those latter effects in more detail when I talk about the physical properties of whale and the principal components of freshwater contents, if I have time. Okay, so, okay, let me talk a little bit about the bathymetry of Simpson. It's shown here from a geological study published in 2008 by Chris Knoll of Texas A&M. And the higher resolution imagery is obtained by swath bathymetry, and that uses both down-looking 250 kilohertz transducers and a side-scan sonar to obtain full bathymetric coverage. The bay is comprised of three compartments here. Basins. We have the southeastern arm down here, the main western basin over here, and to the north, the northern arm. Now, each of these basins differ somewhat in its bathymetry. I'm not talking much about the southeast arm, so I'm going to just mainly focus on these two basins respectively. But this western main basin is separated by this relatively shallow sill, but it goes from depths of about 30 meters over here to the west into a deep area of 60 meters here. But there's also kind of an S-shaped curve to the basin, and some of this bathymetry may be important into the mixing in the deep water column by internal waves that travel through the fjord. The northern basin is separated by this real shallow sill, but there's two deep channels around this, one at about 30 meters to the west, and to the east it's about 40. And they're pretty important because when the flow comes out of this arm, the local vorticity caused by this creates a cyclonic circulation around that reef. And it turns out that's probably a pretty important mechanism in exchanging water, particularly if we have larval fish moving up in, plankton moving up into the fjord. They can draw them up into the northern arm. So I'll talk more about that when I get into the currents. So Simpson's watershed's relatively large. It's about 170 square kilometers, and the maximum elevations range from about 1,200 to 1,500 meters, so there are alpine glaciers within the upper watershed, and they drain primarily into the northern basin. But in comparison to the Rude River, the watershed in Nelson Bay, is the glacial watershed still relatively small, as depicted coarsely on here in this Google Earth image. So that large watershed size at Nelson results in mesoscale advection of glacial water westward past the Channel Islands, and at times this enters into the mouth of Simpson. So here are some examples of that. Looking westward from the Channel Islands in June 2007, you can see the glacial plume here. And in 2011, in August, this was a shot looking back from Simpson towards the east, back towards Cordoba. Now, when this water enters into the outer basin of Simpson, it can create both density fronts and subsurface freshening, leading to higher integrated freshwater contents in the outer basin. However, the main periods of freshening in the summer tend to occur in the late August, when storms cause an increase in rainfall that combines with discharge from the watershed. Now, there are 3 sub-watersheds at Simpson, shown here. This is an image from Knoll et al. 2008. And you see the main watershed here is drained all into the northern basin. And very little water enters into this main western basin. So most of the fresh water that comes out of the system comes from this northern arm, or it's infected in from Nelson into the mouth. One thing that he has here, this is done by GIS, and I'm not sure what the date is of these alpine glaciers that he put in here, but you can see it appears that they're reduced in scope in comparison to a few decades ago when this was done, when I did this paper in 2001. So there's probably less glacial water coming out of the system now, and I've been noticing that on my surveys because it doesn't seem to be as turbid with glacial silt. When we get a lot of rainfall, for example, like in 2011, the water looked like it was mostly terrestrial runoff. It was more brown than it was gray with glacial silt. So I'm wondering how much these glaciers really have retreated now. We're not getting as much runoff into this watershed as we used to. So I wanted to show a few results from the C program for Simpson before going into the more recent research results. So during the C program, these are the instruments that I used to do research, and use a standard CTD, Seabird 19 CTD, to get vertical profiles of the water column for temperature and salinity. And of course the CTD stands for conductivity, temperature, and depth. And we get the salinity out of the conductivity and the temperature and the pressure out of the equation of state. So they get salinity from an algebraic algorithm for that, and the equation of state gives us the density. But the other data I collected were with a RD Instruments 150 kilohertz broadband ADCP to collect data during occurrence on different tide cycles. And the other data were collected with a Chelsea Instruments Aqua Shuttle, which was tow-yowed to get a continuous vertical profile of temperature and salinity. And the reason I had to tow-yo the instrument was, first, we couldn't get it fast enough to fly on its own inside these fjords, and secondly, to do that would have probably invited a disaster, having it crash into the bottom. And I couldn't get as fine a resolution either. Manual tow-yoing was the only real way to go.
What is tow-yoing?
That's where you just let cable out of your winch, bring it in, so you're just letting it go back and down. So as the boat goes, it goes back and forth like this. So that's what we call tow-yoing. You're towing it and yo-yoing it at the same time. Okay, so this is just a summary of some of the results from the CTD work. And let's see. Some of the main points here are that there's a large interannual variation in the heat and freshwater input, which is quite common for this region. And the limited surface freshening in 1996 that you see here, this was due because of the much drier climate in that year versus 97. When storm activity picked up in late August, we got a lot of heavy rainfall. So in addition to that glacial runoff from the watershed, we ended up with quite a bit of freshening here compared to the previous year. So the bulk of the summer freshwater input at Simpson historically has been coming in later in the summer because as rainfall drops through the early part of the summer, you just don't have as much runoff in the watershed. The vertical mixing proceeds pretty rapidly once you go past these summer periods. You can see that with these. There's no vertical gradient in the water column here. It's just progressively getting colder and colder, and the salinity mixes pretty rapidly once the freshwater input drops. And we get surface cooling, so eventually we'll get some thermohaline turnover of the water column, which is a mixing because of the cooling of the surface water becomes denser. It's also saltier, so it tends to want to mix downward. At Simpson, this process operates pretty efficiently and rapidly. Dual controls. It's a little slow for you, so just bear with me. Now, I hope you can see this. It's going to be a little bit washed out, but this is also from the C program. And what it's showing is two separate flood tides. And you'll notice that the pattern of the flows differ quite a bit. Now, the reason for this is that these were done on two different portions of the flood tide. For example, this one here, which shows this jet flowing into the main basin, it's a very prominent jet, and this anticyclonic eddy at the mouth, that was done probably near the very beginning of one of the flood tides when these jets begin to develop. But over here on flood tide, this is 1, this was 2, and this was flood tide 1. This one was done later in the tide, and what happens then is even though we still get this outflow from the southeastern arm, the flows up inside the basin slack off. And the reason this happens is there's an interference by the internal waves that progress up into Simpson, causing reversals in the water column. And this is going to become much clearer when I show you the pattern of flow from the more recent data, because I've got much higher resolution data and it covers more portions of the tide cycle. Okay, as I said before, there are fronts that develop outside here at the mouth of Simpson, and this is most likely coming from Rude River water. This is lower density water and it's slightly warmer. But up in the main basin, then it's colder and it's saltier. And you notice that it's on both sides of this sill. The possible reason for this, all right, I'm going to go back because that darkened that slide. But the possible reason for that is that there's an internal wave that builds on this, over the sill, and it propagates in both directions. And the reason that it can propagate against the tides is that the background flow is slow enough relative to the internal wave speeds so that the wave can progress in either direction on the tides. So the methods that were used here in the more recent data involved some intensive ADCP surveys, and the data for the currents were collected continuously over 24+ hour diurnal periods in the summer of 2007 and 13-plus-hour semi-diurnal periods in 2008. The hydrography stations were occupied on every other run of the ADCP, and that gave me about 4 to 6 repeated sets of casts that included fluorescence and turbidity. And here's an example of the instruments. You can see them very well here, but that's a towed 600 kilohertz ADCP, and it provided a much better resolution because of a much higher frequency of the ADCP. These are the transects that we ran. I only came out of the southeast arm of the first set of transects, went back up the basin, and then came down the fjord, and then returned back across the mouth and back up the basins. And then the vertical TS profiles were again collected with an SP19. Now I also collected temperature and salinity with some moored instruments, moored CTDs and CTs and thermistors. And they were moored in the inner and outer basin. And meteorological data was also collected, including air temperatures, winds, and precipitation. And they were collected on the outer surface buoy in the main basin and on a shore station located on a small island. So here's some examples of the two buoys that were used. This is the one out at the main basin. It has the weather station attached to it, located right here, just up inside the sill. And then the other mooring is located just beyond the shallow reef up here in this deeper part of the northern arm. And unfortunately, these are washed out something. You can't really see it very well. This is the island where this weather station was erected. I can just see the buoy pole, or the pole for the weather station right here. Yep, I can see there's a lot of light coming across the screen. Now, just to start out with, the winds collected there at the mouth show a pattern in which there's a diurnal wind that tends to blow up the fjord. And what I have here are the original winds that have been rotated to get a long fjord component. So this is showing the component of the wind that's mainly going up the fjord and down the fjord. And when we don't have this diurnal component of winds, and if we have a storm, then the winds tend to blow out of the fjord continuously. At night, though, after we have this diurnal wind blowing in, there tends to be an outflow from the fjord. Okay, so I'm going to go through the pattern of the currents here. I hope you can see this very well because it is a bit dark. But I'm going to go through the full tide cycles. And what we're going to have is the surface currents at about 2 to 3 meters here. And over here in this box is what portion of the tide that the currents occupy on these transects. That's through the whole set of transects. And up here are the winds going into the fjord during the July survey. And by the way, this was the only survey where I actually was getting data on one of these diurnal wind periods. All the other surveys, the winds were relatively weak, and I did not have this pattern. So if we go starting here at the beginning of this flood tide, we see that there's a flow coming into the fjord. It's a jet that's moving in. There is the reversal moving out here, and it's probably creating this anticyclonic eddy at the mouth that I showed you from the sea program. And there's also a flow accelerating across this reef, moving up into the northern basin. But what happens as we move farther into the tide here, even though this wind is still blowing in, we're not seeing any effect of the wind in this layer. If there's any effect in the wind, it tends to be in the very near surface layer. The buoyancy of the water column tends to prevent the wind from transferring its momentum downward. And this has been found in Norwegian fjords as well. So what I'm getting here is this water is very slack in the middle of this flood tide. It's actually reversing and coming out. There's that flow coming out of the southeast arm that I showed you earlier from the sea program. So what's causing this is probably these internal waves moving in, which is causing a divergence region in the middle of the fjord, forcing water to go back out. Now this is a pretty common phenomenon because through the tides we usually see these rips, and they're related to the internal waves moving through the fjord. But they're also propagating and changing so that they make it through one phase of the tides and dissipate, and then we see another set coming down through the ebb. So this is moving into the next transect, and we're now at the top of the flood tide. And I know it's hard to see, but there's actually the beginning of an outflow and ebb up here. You still see the flow coming out from the southeast arm. It tends to want to continually flow at the surface out of this basin here. But as we move further into the ebb, that flow accelerates. You can see this very well, but that's an increase in the current vectors coming out. But what happens down here at the mouth is there is a reversal moving in across this sill. Then as we go farther into the ebb, you start to see this cyclonic eddy develop around the reef. Now this is a pattern that occurs on every ebb tide that I've collected data from. Now, as we come down the fjord again, we start into the next flood tide, and here comes the tidal jet moving in. The cyclonic flow is still intact at the end of the ebb tide, but the jet has now begun to move inward. So if I go through the other set of tides, we'll see the same pattern. There's the reversal during the middle of the tide. There's the ebb flow starting to come out. There's a stronger acceleration of that flow across the reef because we have a larger ebb tide now, larger prism moving water out now. And then there's the cyclonic flow developing around the reef. And then this is the beginning of the last flood tide of the whole set of transects. And you can see it is a really strong jet that's moving into the beginning of that tide. So now, before I talk about the transport calculations, I wanted to briefly discuss how I went about filling in the bottom profiles of the currents here. You can't see it, unfortunately, but there was a line showing where the ADCP data, there's a blanking distance at the bottom because of the bottom echo tends to interfere with the returned echoes because of side lobe interference. And so the ADCP has a blanking area, and it also involves poor data quality when you reach the very limit of the ADCP. Well, to fill that in, what I use is a standard logarithmic profile based upon the friction velocity near the bottom. And what this equation shows is the friction velocity divided by the von Karman constant multiplied by the log of the ratio of the depth relative to the roughness parameter at the bottom. That will give you the flow logarithmic profile as you come to the bottom. The friction velocity here is determined by a stress at the bottom divided by density. We take the square root of that. That stress is given by a pretty standard equation, which is the density multiplied by the drag coefficient, the square of the flow. If you put that back into this equation, then U star, friction velocity, just becomes the square root of the drag coefficient multiplied by the current. So I was able to just put that back up into this equation, and that gave me these bottom profiles, and you can see that that filled in this very well. I wish you could see that bottom line, but I'm trying to trace it right with the pointer. That would have been all blanked out with the original data. Okay, so with the transport calculations, I'm going to show them for 3 sections. The first one starts down here across the mouth. It goes across the inner part of the sill, and the other then goes across the entire sill, and the next one is just to the north. So that's section A, it's followed by section B, and then section C. Okay, I got to put myself down here. Okay. All right, so starting with section A, We're moving across the beginning of the flood tide again, and this bar right here shows us where we are in the tide and how much of that tide is occupied by the transects across that section. Also, that bar is showing the barotropic flow. Now, the baroclinic flow is about equal to this. These tides are balanced, so that the entire flow is just due to tide here. There's not an additional baroclinic component that's going in addition to the tide. But when we go up to the sill proper, that's where we start to see an excess flow moving across the sill. The red is the baroclinic, the blue is the barotropic. Now, what those are, the barotropic is the amount of flow that's moving into the fjord based on the tide flows themselves. Now, the amount of water that's going into the fjord cannot exceed that barotropic component because that is determined by the height of the tides. So when you get this baroclinic flow that is in balance with it, it means that somewhere on the sides of the transects there's more flow moving out of the fjord to finally create a balance for the whole system. But this also means that there's a pulse of water being pushed in by this baroclinic flow that's being pushed back out on this side. Now if we move up to section C, see that they're pretty much in balance at this time. But if we come back down the fjord and get section C again, they're not. The baroclinic is now higher than the barotropic. You still have a large imbalance across the sill. And then down here at the, coming back across section C again, the baroclinic is even stronger as an imbalance to the barotropic. But the other thing that's happening is the surface jet is degraded into a series of subsurface flows. And this is where the waves interfere with the jet and cause it to degrade into these subsurface flows. So on the ebb tides, they are pretty much imbalanced. Both the baroclinic and the barotropic are pretty much imbalanced throughout the ebb tides. So here we are coming back across section C, and it's section B. But notice what's going on here is the flow coming out has become a subsurface jet. And the reason for that is that there is a flow moving back in over the sill at the surface. Now over section A, we can see that jet still moving across the outer sill, and that's the primary mechanism in which water flows out of the fjord. It's also flowing out over this deeper trench, and the flows here in this measured section are pretty much in balance. Now if we go back up the fjord to section C again, we can see that they're still imbalanced, and the flows now are split into two sections going out. And when we go into flood tide 2, the jet develops again, and we can see it's got a prominent structure in the water column, but throughout these two transects down here at the mouth of the fjord, the baroclinic flows are in balance with the barotropic, so there's now a pulse of water being moved in that's being pushed back out on the edges of the transect somewhere. But somewhere in these sections, those flows have got to come out in order for this to balance. And like I said, it can't exceed the volume inside the fjord based on the tide level. That's the barotropic flow. So what I did with this is I integrated these flows after I determined the net inflow or outflow from the two components. And again, it's hard to see the slide, I apologize, but the barotropic is here, the baroclinic is up here, it's higher, but the two sum to the total net flow coming in. And on these flood tides, that flow is greater than the ebb tides in terms of the baroclinic. And the barotropic here is pretty much the entire flow, so you see a zero right here where the baroclinic is, because it's balanced with the barotropic. Now, in the other 2 months of 2007, that pattern continued, although in August it's similar to July because we have higher stratification, But in June, when we have limited stratification, the imbalance is there, but it's just not as strong. But when I take the average of these flood integrations and then the ebbs and sum them, I get an estimate of the flushing rates. And this list down here in this little table gives us those flushing rates. You can see that in July, with this big baroclinic imbalance, the flushing rate is really high compared to the other 2 months, particularly for June. It's over 1,360 cubic meters per second. This results into a flushing of that whole western basin in a period of 2.3 days. In August, it's about double, but in June, because of the closer balance of the currents, it takes closer to 16 days. Now, that's just an example of what would happen if these flows were to continue over time. But anyway, the point of this is that what's going on here at Simpson is that on these tides, there's a baroclinic flow on the flood tide that's producing a pulse of water in that's not counterbalanced by a flow going out in the ebb with a pulse going back into the fjord on the ebb tide. So we're getting a continuous transport of water into the lower basin of Simpson. And then what is transported up on these jets or in the subsurface flows could end up going up into the northern arm by that cyclonic eddy that develops around the reef. So those flows appear to form a pretty important part of the flow into the fjord, bringing larval fish, plankton, and nutrients inside, and then bringing the larval fish, the H0 herring, into the inner basin of the northern arm and retaining them there. The deep flow tends to just reverse under those surface currents, and so the larval fish, if they change their buoyancy and go down to the water column, they can just ride that current back and forth and never come out of that northern arm. Okay, what I wanted to go into next was some evidence of the internal tides and waves from the hydrography data. That here. And I'm going to show just a series from the CTD cast. These are vertical sections of the salinity, which, because that's very close to the density up in our region, density is primarily determined in the summer period by the salinity of the water. So this is pretty much the same thing as the density, but the same pattern showed up on the thermocline as well. They were both pretty much in phase. And on this side, we're going to see again the period that the section occupies on the tide. And here I've got the winds again through the July cruise. So if we start to go through here, this is on this middle of the flood tide, we'll see a wave start to develop over the sill here. And then it dissipates inward. Now on the ebb, we get a large wave developing over this sill here. And then it can dissipate, it can propagate and dissipate inward as well. So here we have another wave developing around the sill, propagates inward. And we're now into the August data. There's another wave, and it's dispersion into the fjord, into the inner basin. Another wave. Now, not only do the waves change the relative level of the pycnocline in the fjord, they also influence the distribution of the phytoplankton. So I'm going to go through the same series of slides, but we're going to look at fluorescence. You'll see that this is a pretty wide band of fluorescence initially, but when we go into the ebb, it turns into a narrow band. And out here we see it, the flood tides is going out into deeper in the water. It's going into the deeper in the water column, so it's becoming more diffuse. And then we go back to the next tide. This is probably on an ebb, and another flood, another ebb, another flood. So anyway, the point is that the distribution of these phytoplankton layers can be affected by these waves. So when you go in and measure it, you're not always getting the same distribution. The same thing goes with the TS data as well. Now this slide here is just something that I wanted to talk about. It's a study of internal waves in a Norwegian fjord by Velisenko et al., and it's a modeling study that looked at water exchange from tidally generated lee waves, and they used a non-hydrostatic, non-linear numerical model. And just to let you know what that means is that a non-hydrostatic model is one which does not use what we call a hydrostatic approximation for the vertical currents, because the vertical currents can be just described in most models by just the vertical pressure, and that's the hydrostatic approximation. But in a non-hydrostatic approximation, there is a vertical exchange, whereas in a hydrostatic flow, it's mostly all horizontal. Now this equation down here is used in their paper. It's the Euler equation, and what this is just the total derivative broken down into its two components. This is the local time rate change, and this is the effective rate. And if we expand that out, you'll see that it's this background flow multiplied by this differential gradient in the x, y, and the z. Now this is a pretty typical equation for all the equations of motion. If we were to put the full equation in, it would be balanced by Coriolis, the pressure gradient, and then the turbulent dissipation. So what happens is the barotropic flow over the sills within a stratified basin can generate these possible internal wave types based on this local time rate and then the effective term. If the first term dominates, what you end up with are these internal tides, which is what looks like mostly occurs in Simpson from the hydrography data. But if in the first modes of those internal tides have wavelengths on the orders of tens of kilometers and frequencies on the order of the semi-diurnal tide. But if the second nonlinear term is important, then this can result in steady and unsteady lee waves, which then can propagate through the basin, but their wavelength is much shorter. It's on the order of the bottom topography. And the evidence that we see in Simpson during the cruises indicates that these waves probably do occur. And they build by extracting energy from the tide flow. So the main message here is that the effects of this nonlinear term, it can lead to transforming the tidal wave into a baroclinic board. Well, that's exactly what we see at Simpson. It's a baroclinic jet that then degrades because of the waves, which then develop as a set of internal waves and causes that flow to become a subsurface flow. So the structure of the flows in this fjord are very complex, and not a simple tide flow in and out at all. They go in layers, and because of these internal waves, we see a lot of these layers moving into the fjord. So now I want to cover the evidence of these waves in the thermistor data. So this is a plot of the data itself from the thermistors from 10, 20, 30, and 40 meters. You get this outer basin here at mooring A. Mooring B is going to be in the inner basin. Now what I had to do here was that first I had to remove the low frequency component to just look at the tidal components of the time series. So this is the high pass version of these time series. Then what I had to do was remove the fluctuations in the thermocline based on the tide itself. And that was done by taking the CTD data and the deep CTDs and looking at the pressure variance to get the height variation, and then looking at the gradients from the CTD data itself in June, July, and August, and then just interpolating that through to get the amount of change that would occur just based on the tide itself rising and falling. Then the residual from that becomes what we see as internal waves. And so as you can see, the residual, what we have is a fairly prominent set of waves. And because the water column is less stratified in the deeper area here, 40 meters, 30 and 40 meters, those waves can develop much higher because there's no buoyancy to restrict their growth. Whereas up here, closer to the surface, the buoyancy frequency is higher, so they will oscillate a little faster, and there will be more, and there will be a restriction in how high they will develop. Now, these are power spectra of those data. And the reason I did this is it involves a Fourier transform so that we can look at from the time domain to the frequency domain, and it gives us a general snapshot of what are the important frequencies in that time series. Right here is the semi-diurnal peak, and here is a lower frequency peak, and that is actually diurnal. If you can see the scale better, this is in cycles per hour, so this is in the semi-diurnal, and this is the diurnal. Now this lower spectra is a variance preserving spectra, and what that is we take this power spectra and divide by the frequencies of the data of these plots, of what is shown in the spectral plot, and that gives us a much better picture of the importance of these spectra in the spectra, the frequencies in the spectra. And so in both of these arms, you can see that the semi-diurnal is the primary frequency with which the waves are oscillating, but there are some higher frequencies in both basins as well as a diurnal frequency. Let's see, so this is basin. So that's, again, it's the inner basin, and we see the same pattern in the inner basin as in the outer basin with the diurnal frequency, but no, we don't see as much of the higher frequency wave. Okay, I'm just going to go ahead and go through the rest of these because they're all pretty much the same. And now I'm going to talk a little bit about vertical diffusivity. And, okay, the vertical diffusivity, this is from a study of some Norwegian fjords, a whole series of them by Styggebrat and R in 1989. And I decided to duplicate their methods just to see what would come out in the ratios of the amount of work that would be imparted by internal waves to mixing the deep water relative to what density changes really take place. So are we seeing really mostly diffusive processes causing changes in the density, or are there advective processes? And as we'll see here, the advective processes are the most important in making the changes, but the waves interact with them, with the advection of different water masses. So in calculating the vertical diffusivity, which has to be done first before getting the work equations calculated, it's done by taking both the spatial averages of the vertical gradient density multiplied by the integral below sill depth at the various depths of the change in density over time. Now, it requires that you have hypsographic data over the depths, and I tried to estimate those from nautical charts. The surface area for the fjord itself, for both the inner and outer basins, I took from Knoll et al. To 2008 because he had done that with GIS. And then the calculations were made from the CTD data from the various tide phases. But I'm just going to show this result between July and August because I think that really tells the whole tale. So here are two calculations that are done with the vertical diffusivity to get this net work against the buoyancy forces by the internal waves. And then this value here is the amount of energy that could be supplied to the internal waves by the tides themselves. And then this is a Richardson flux number, which is based on the ratio of these two. So just to give you an idea of what's going on, this is the work equation here that's derived from these equations utilizing the vertical diffusivity here in this integral with the buoyancy frequency and the area at each depth. This is the equation which gives us the tidal energy. The numerator involves the density and the frequency of the tide and the amplitude, and then the area of the fjord. And this is the internal wave speed given by this equation, which is a pretty standard equation for 2 layers. And then the denominator is the area of the sill multiplied by the total depth. And then, of course, we get the ratio of those two here. So what we get here is an extremely high ratio, indicating that the amount of work that's supplied to the internal waves far exceeds what could be coming from the tides. And so that indicates that what's causing density changes are not just diffusive and turbulent processes in the fjord, but it's infection of different water masses moving in. And I'm going to show those on the time series analysis. So I'm going to go into that now. And once again, here are the wind speeds in 2007. And in June here, what I have are just the speeds, because this was taken from the buoy. I didn't have the shore station set up yet, so I couldn't get the vectors. But what I have are the speeds. And you can see periods where the diurnal winds are occurring. It's just I don't have them in these along fjord components as I do in July and August. So here is a Fourier analysis of the wind series itself. And this peak right here, which is really prominent in the variance preserving spectra, is all diurnal. But there is also a slight diurnal peak as well. And this is in, I believe this was in July, and this is August, yes. And this semi-diurnal peak is probably associated with those downfjord winds that occur at night. Because that would create a semi-diurnal frequency. But as you can see, it's not very large in amplitude. So the really important winds affecting Simpson are these diurnal winds that blow in during the day. Now, they are caused in part by sea breeze effects. So our maximum winds will blow in when we have a lot of sunshine in the summer, and we get westerly winds blowing in from Orca Bay. They turn right up into Simpson, and they're pretty strong. So now what this is a wavelet analysis. And what wavelets are, if we take, as where the Fourier analysis gave us a general picture of the important frequencies in the time series, the wavelet analysis gives us a picture of where those frequencies occur. And I don't know if you can see this very well, but the important frequencies, the statistically significant frequencies, are right here in the diurnal band here. And this shows where in the series they occur. This is the variance of the series, and this line here is the 95% confidence limit. So we can see that in early July, there's some pretty strong diurnal winds that are significant. Their strength, but there are these winds right here. And of course, we have a storm here, which creates the outflowing winds, and then we return to diurnal winds here. Okay, this is August. Same period here in the middle of the month, and this is where the significant winds occur, and here they are in the variance of the series. Now, moving into the TS data in winds, these are the temperature and salinities at the near surface moorings, and then the deep sensors at 40 and 70 meters in the outside basin and the inner basin. And this is at 3 meters in the outer basin and 2 meters in the, 3 meters in the outer basin and 2 in the northern arm. And then this is the same for salinity. What we wanted to do was take the low pass filter data, and then I overplotted them here. And what's happening is in the surface series, they're pretty much in phase with one another, but there are periods when they go, they reverse relative to one another. In other words, where the temperature goes up, the salinity goes down because it's fresher water, and then where the temperature drops, the salinity goes up. So what that represents is there are periods when the marine source water starts to change outside the fjord. So that water that's being infected in is either coming from the Brood River when it's warmer and fresher, and it's coming from Prince William Sound when it's coming from the west. Now there's a lot of coherence, turns out, when I did coherence spectra between the inner and outer basins, indicating that there's a lot of surface exchange which is being forced in part by the winds. It turns out that the wind series also shows some coherence with these temperature and salinity changes in the inner and outer basin. But the deep sensors are not coherent at all, which indicates that they are separated. And if we look at the wavelet spectra for the near surface sensors, the only significant variance in this time series, this is the original series, is given by the low frequencies. And that's down here. This is where the significant low frequencies are in the time series, and this you can see even better here in the variance spot. Same thing occurs in the salinities in the near surface. Now the deep sensors, however, have a different pattern. As we get farther into the months, we see that in both basins, this is the semi-diurnal frequency here, as well as the low frequencies, they're significant statistically as well. So there are some fluctuations in the deep water that appears to be going on in association with the tides. And this is the temperature and salinity in July and August. Again, you see the same thing for this. Actually, this is for the salinity series. Let's see, one before that was temperatures, and then the salinities. Same thing occurs. There are periods when the semi-diurnal frequency is significant, low frequencies are significant, but inside the inner basin, in the deep water, there are only a couple of periods where this is significant. And it's these periods where you see these perturbations here and here. So I'm going to summarize this in some conclusions. So the currents in hydrography at Simpson were measured in the ADCP transects and CTDs over diurnal periods and by moored temperatures and salinities and winds at net stations. The water exchange process is driven primarily by an imbalance in the baroclinic flows, and that occurs during flood tides. The variation of the tidal prisms and stratification result in these differences in exchange rates and the flushing period estimates. And the internal waves also form a part of the exchange mechanism, and they're generated by the stratified flows, the tidal flows over these sills. And the nonlinear effects due to variation in sill bathymetry may also generate lee waves, and they'd be at a frequency that's just about nearly twice the semi-diurnal. And when I looked at the internal wave speeds and what it would take to go through these basins, if they're pretty much in line with what we see on the surface during the tide phases with those rips that move through. So I'm pretty much convinced, even though my study wasn't directed specifically at analyzing internal waves, which we'd need with a sophisticated model, I'm convinced that those lee waves probably do exist. So the winds, they're primarily diurnal in frequency. They play a role in surface water exchange, but it's less clear as how they influence the deep flows. What may happen with the deep flows is when we get this surface inflow that's held up in that near surface layer, it may create some downwelling around that inner sill. And when that happens, that can cause flow to go back in the deeper water column, out and in and through those channels. So it may be these diurnal winds are what are forcing some of that water exchange into the northern basin, which is normally isolated. So anyway, I think I'll probably just quit there. I think you guys have had enough of that. I'm going to end with a little bit of a slideshow. Because all of this stuff here is in my paper. If anybody's interested in it, I can show you later on.
Why don't you go back to the conclusions?
Okay, well, This would probably be more clear if I went through that part at the top, but okay, so the circulation in these small basins is driven mainly by tidal prisms and winds, but the latter, they're highly variable depending on the local topography, because the local topography affects these geostrophic winds that are coming through PWS. And that's pretty obvious in those winds at Simpson, those diurnal winds. Those are totally ageostrophic winds. What do I mean by geostrophic winds? It's the same thing as geostrophic currents, large-scale geostrophic currents in the ocean. They're created by a balance of the pressure gradient with Coriolis, so that the flow has to move along the pressure gradient. So when we look at winds out over the Gulf, when we look at a weather chart, look at a barometer plot of the winds, and you'll see that you've got like a bullseye during a low pressure system. Those winds are basically following all along the pressure gradient. An ageostrophic wind will change because it's not bounded just by the pressure gradient itself. So these baroclinic flows can be markedly modulated by maximum depth and the presence of sills through the action of these internal waves. And by the way, if I'd have shown the rest of the presentation, you'd have seen that Whale, the isopycnal surfaces always tend to be relatively level. It's a deep fjord, a 300-meter open basin, and it doesn't generate the same internal waves as Simpson and Zykov do. Now at Simpson Bay, in one location at least, there's an imbalance in the baroclinic tidal flows between the flood and ebb tides, and that results in these net inflows and flushing of the main basin. And it looks like that occurs on a quasi-continuous basis in that basin. So given these constraints, the main and outer basins of most of these fjords are essentially inland extensions of the sound, and they behave like stratified embayments, or with complicated currents in some cases, as I showed for Simpson. But the secondary silled inner basins, they will exhibit more fjord-like dynamics. So if we get a real separation in a lot of these small fjords between these outer and inner basins, especially when you have a shallow sill. So anyway, I was going to show a few slides from the programs. There's Scott at the helm of the old Orca Challenger, which we used in July and August of 2007 in order to collect all these data at Simpson. And these were monotonous transects, believe me, over 24 hours. Scott can attest to that. Broken occasionally with CTD casts, but everybody was smiling because we had great weather. So here's that diurnal wind I was talking about blowing in the afternoon. We had clear weather and we had a pretty good wind blowing in, but that wasn't the maximum winds. Those peaks in wind speeds that I showed you in June, late June, those were some really substantial winds blowing into the fjord. Okay, here's James Thorne and I. We're putting up the shore-based station. Now we can get a better picture of what that looks like. It's out there on that little island just to the west of the mouth of the southeast arm. It was a really ideal spot for collecting these winds. That's Brad Reynolds. He's holding up the buoy I designed and had built by Lenny to do the Met station and the TS data. But I put a tether on it out there, and that was designed to keep the thing upright in the water column against the currents in the wind, and it did a very good job. It's located right at about the center of pressure for the whole mooring. And then here's the mooring itself. Andy and I talked about it, and we thought that Rick Schultz had these old Danforth anchors that would be really good, about 70-pound anchors. And we thought, why not throw these out there to hold these moorings in place? So I put about 30 feet of chain, 3/8 chain, and then put these big lengths that came from the sweeprider. That's about 90 pounds of weight right there. And it held the entire mooring down. That buoy never budged 1 inch through the whole summer. And that's Andy. We're bringing it in at the end of the season in August. Yeah, this was down at Whale Bay, and James and I went up onto the Pleiades where we put up a weather station there. And then, because of the ice coming out of Icy Bay, I ended up putting on an ice guard onto my mooring down there for both the instrument and the buoys, just to prevent a puncture and loss of the buoy, the surface buoy itself. And now I'm going to show a few slides from the old sea program. This was me back in '94 with long hair, and that's Jeff Snegden. He caught this big 100-pound halibut off the Wavelet. We were down off the northern side of Prince of Wales Pass. I jumped down there with him to help land it. In '96, we put some pots out over the mooring in Icy Bay, and boy, we got a nice catch. So we put them out the night or the day before we went out to do the transects, and we spent all night and part of the next day doing these transects. They went back and got this nice catch. Herb Jensen was really jealous when he saw this too. Oh, it's all washed out. This is a motley crew. That's Sam O'Toole, Lauren Tuttle, who used to work with us at the Science Center, and then me. And this was in 1998. I think it was up in Icy Bay. This is in '94. This is a fishing game fry crew, and I call them the fried crew because they had been doing this for days on end, and they've been going from dawn to dusk trying to trace these juvenile pink salmon smolts immigrating out of the Sound. Margaret Powell's kind of staring at me like going, oh, not again, another day of this. There's Annette and Holly Janka. We went over to Lower Herring Bay. We got off the boat. Occasionally we did get off the boat. We got a chance to go out and see how beautiful these two sites are. And there's Bill again, and he's clowning around with our catch in Icy Bay. And this is the Chiniga Glacier. This is in June of '94. And I threw these in too just because it's so intricate when you get the melting of the ice in these sites. So here's a berg in the mountains and a berg in the fjord. And this is just an intricate pattern resulting from the gradual melting of the ice. And when I got ashore at Lower Herring, I did get my zoom lens out and did a few shots of some wildflowers. There was the shooting star, chocolate lily, and some violets. And of course, we had beautiful sunsets every cruise, right? It's always nice in Prince William Sound. So anyway, that's it. And thanks for coming, for listening. If anybody's interested, I can go back and show you this stuff that I was showing for Zykov and whale. But essentially, what I was going to show was that the evidence from the Opera Shuttle data shows that these internal waves do probably occur in Zykov Bay, and they do influence the hydrography. And there is evidence of water exchange into the inner basin where the H0 herring frequent the fjord. Any questions? I'm glad to address them.
I wouldn't know what to ask.